Alright, let's look at the next topic. So this topic we will study about calorimetry. So calorimetry is about study about heat change. So we have two calorimeter. One of them is known as bomb calorimeters. The other one is known as a coffee cup calorimeters. So later we'll look in detail about these two calorimeters. Okay, look into more detail about the definition. So what is a calorimetry? So calorimetry is measurements of heat change. And we have two very similar terms. One is known as a heat capacity, the other one is known as specific heat capacity. So the first one is a specific heat. So the specific heat of a substance is the amount of heat required to raise the temperature of 1 grams of the substance by 1 degree Celsius. So we are assigned a symbol S for specific heat. Alright, so next time you see the symbol S is known as specific heat. So this one is very specific, means they are only specific 1 gram of the substance and it must raise the degree Celsius by 1 degree Celsius. So as you can see, look at the unit is joule per gram dot degree Celsius. While the second term is known as a heat capacity. Heat capacity. So heat capacity, we actually assign a symbol known as a C. Alright, the heat capacity of a substance is the amount of heat required to raise the temperature of any given quantity of the substance by 1 degree Celsius. So the only difference that for specific heat is must be 1 gram, but for heat capacity is any given amount. Both have the similarity of raising the temperature by 1 degree Celsius. So if I'm looking at the units, so heat capacity will have the units of joule per degree Celsius. So based on this, we actually can form a formula. So it's known as a C equal to ms. So as you can see, if I write down C equal to ms, the first one is known as a heat capacity. So with the unit joule per degree Celsius equal to m will be mass, so it will be in the unit of gram. And then you're going to multiply it with the S, which is a specific heat. So we have joule per gram dot degree Celsius. As you can see, we actually cancel, we get back the same thing, joule per degree Celsius. Alright, done with these three different definitions, calorimetry, specific heat, and heat capacity. Next, we look at another important terms, they call it the heat. So heat, we are assigned the symbol Q. It's a small q, not a capital Q. So we have two formula to quantify the Q. First one is C delta T. The second one is MS delta T. Alright, C once again is the heat capacity, M is a mass, and S will be the specific heats. So delta T as usual is a T final minus T initial. So since the delta T, this part here can be plus, it can be minus. So therefore, our Q can be plus or minus. So if the Q is more than 0, in other words, positive, so then we say that the heat will be absorbed into the system. So this is known as an endothermic process. On the other side, when the Q is less than 0, this one means that the Q is in negative. So it means that the system is released heat to the surrounding. So this is also known as an exothermic reactions. Alright, look at this table on the right side here. So we have a list of many different substances with their own specific heat. So their unit is joule per gram per degree Celsius. So I just pick one for example. The famous one, of course, will be your H2O. So you look at the value, which is 4.184. So how to translate this into a meaning? It means that if I want to raise 1 grams of H2O by 1 degree Celsius, so you need to absorb 4.184 joules of heat. So this is why we learn specific heat. Alright, so most of the question are using water because water is universal solvent. So and you don't need to memorize all this value because in the question they will give us. So like for example, H2O will be 4.184. Right, next. So here are some questions for you to test your understanding. Determine the heat capacity for 60 grams of water. So heat capacity, once again, the symbol is C. So according to the formula, so we have one formula which is C equal to ms. Alright, M is mass, so of course we put 60 gram. Specific heat of water is given, so this one is 4.184 joule per gram dot degree Celsius. So we calculate, so we get 251 joule per degree Celsius. So this is very important that every student must put in the value and also in the correct units. Okay, another question here. A 466 gram sample of water is heated from 8.5 to 74.6 degrees Celsius. Calculate the amount of heat absorbed by the water in kilojoule. So they want heat. So heat symbol Q. They actually tell us that the answer is Q is absorbed. So endothermic. So the Q answer must be in plus. The unit they want is kilojoule. Okay, to find the heat, we have two formula. First one is Q equal to C delta T or Q equal to ms delta T. So which one to use depends on the questions. So this question actually gives us the mass. As you can see, it's 466 grams. So we are using the second equations. So Q equal to ms delta T. So M is a sample, of course, in gram, 466 gram. Specific heat, so this sample is actually water, so we are using the same specific heat here. So it'll be 4.184 joule per gram dot degree Celsius. The delta T is the difference here. So you always take the T final, which is this one, minus the T initial. So 74.60, you're going to minus 8.50 degrees Celsius. Alright, we have quantified this one. So in calculator, you get this answer, 128.878 joule. And again, you have to read the question properly. They don't want the unit in joule. They want it in kilojoule. So we translate into kilojoule. You get 129 kilojoule. And the answer is positive. So we show that the heat is absorbed. So this one you can see that the heat is absorbed. In other words, this one is an endothermic process. Alright. Okay, next, how much heat is given off? So once again, Q given off means that the Q will be less than 0. In other words, Q will be negative when 869 grams of iron bar cool from 94 to 5 degrees Celsius. So this one, you see that the question will actually give us the specific heat of the iron bar. Alright, so since we are having the mass, so we're going to use the second equations. As I showed you just now, to quantify the heat, we have two different formula. One is without mass, one is with the mass. So we're using the second one, Q equal to ms delta T. So mass 869 gram. Specific heat of iron 0.444 joule per gram dot degree Celsius. Okay, the delta T will take 5 minus 94. The later minus the previous one. 5 minus 94 degrees Celsius. So therefore, we actually get a negative answer. Negative 34000 joule. So put it in kilojoule. Negative 34 kilojoule. Right, next. A piece of copper with a mass of 218 gram has a heat capacity. What is the specific heat of copper? So heat capacity we have here, this is C, this one is a M. Specific heat, so this one the symbol will be S. So you can see MCS, so we have one formula to relate them all. C equal to MS, so we are interesting to find out the S equal to C over M. So 83.9 joule per degree Celsius over 218 grams. So calculate, you will get 0.385 joule per gram dot degree Celsius. Okay, question number 8. Given the specific heat of aluminium is 0.9 joule per gram per degree Celsius. How much heat, Q, question mark, is released when 3.8 grams of sample of aluminium is cooled from 450 to 25 degrees Celsius. So M also given. So from here we can calculate the delta T. So the equation, we are using the one that involve mass. So ms delta T. So the mass is 3.8 gram. Specific heat of aluminium is given 0.9 joule per gram dot degree Celsius. Delta T, we take 25 minus 450 degrees Celsius. Take note that whenever you calculate the heat using ms delta T or C delta T, the T is in small. So in other words, is in degrees Celsius. So we no need to convert into Kelvin. Alright, so with calculator, we'll get this answer. And we convert into joule. So it's 1453.5 joule. So convert into kilojoule, we'll get 1.45 kilojoule. Okay, next we're going to one of more complicated calculation here that involving heat change. So before this, you have to learn two types of calorimeter. So one is known as a bomb calorimeters, another one is known as a coffee cup calorimeters. Okay, bomb calorimeters is quite a layman terms. So in chemistry, sometimes we call it the constant volume calorimeter. All right. Why constant volume? Because you can see that this one we are using the water, so the volume of the water that we use is fixed in fixed volume, hence the name constant volume calorimeters. Why the name bomb? Bomb is something to do with explosions, so this one actually measure only one reaction, which is the heat of combustion. So heat is Q. So normally we write Q reaction, so in short form is Q RXN. So but this one only specific measure heat of combustion. So normally we can just say this one is actually measure Q combustion. So as you know already, combustion is an exothermic process. Alright. So let me walk you through the details of this bomb calorimeters. So as you can see here, we have a calorimeter buckets here. We put inside insulated jackets, and the bucket actually inside we can see we're putting a fixed volume of water. All right, and you will see in the water, immersed into the water, we actually have a bomb. All right, so this one is a stainless steel bomb, and inside the bomb we can actually have a sample cup. So the sample cup is where you put your sample. So and you can see that we are not using any liquid sample or sample in gas. So the sample that you put normally tend to be in solid form. Alright, so the sample, once you put into a sample cup, you can see that actually there's oxygen inlets, so it means that they actually can allow the oxygen to pump inside. Then with spark, we can generate a combustion. So the food is actually explode. In other words, it's burn. So when it burn, it will release the heat. So the heat will be absorbed by the surrounding. All right. So here they put a statement that no heat mass enter or leave the system. So sometimes they consider this one as an isolated system. All right. You can see that actually there's a thermometer here. So this one is for you to measure the heat change. Then we have stirrer. Stirrer is for you to make sure that the heat distribution in the water is even. All right. So for every system, you need to know what is the system and what is the surrounding. So in this case, the system will be actually the food. Normally, we are using the solid as a food. All right. So normally we are putting a food. Let's say we want to find the heat change from burning certain solid, burning certain foods. All right, so the system basically will be your solid that you burn. All right, and the surrounding basically is everything, the sample cup, the bomb, the water, and the bucket, and also the thermometer. So means this is all the rest of the beside the solid that you burn. All right, so what I want to go through here is actually more importantly is actually the formula that you use in calculations. So the Q reaction is actually equal to minus Q water plus Q cal. To put this on, it also means that the Q reactions is actually equal to negative Q surrounding. So the surrounding basically they just put a two major thing here. One is the water, one is a calorimeter. Cal here means calorimeter, the whole thing. All right. So as you know that when the reaction is releasing the heat, the surrounding will absorb the heat. Therefore, you will see a minus. All right, so they're split into two. One is Q water, one is Q cal. For Q water, since you're putting a fixed volume of water, and we know that the density of water is 1 gram per ml, so actually can find the mass of water. Specific of water we know, and the delta T is experienced by the thermometer. All right, move on. Q cal. Okay, different calorimeters have the heat capacity value. So they will give us the C cal, means the heat capacity value of the calorimeters. So the delta T here is also measured by the same thermometer. So we can say that these two delta T actually will have the same value. All right. So you need to remember the formula, and whenever you use Q water, you must use MS delta T. And for Q cal, you must use C delta T. Okay, next we look at this part here. Reaction is actually occur at constant volume. We say that the delta H is not equal to the heat change. So in other words, if they ask you to find the heat, of course we are using this formula. But if they ask you to find the enthalpy change, so students have to differentiate. Heat and enthalpy is two different things, right? So the enthalpy basically are equal to the heat that occur at constant pressure, right? But this does not happen at constant pressure because the pressure will build up inside here, right? But this one happen at constant volume, so that's the difference, all right? But nevertheless, we will just assume that the delta H or the enthalpy change is equal to the Q reaction that you measure. So whenever you have any questions or calculation about bomb calorimeters, if they ask you to measure delta H, first we use this reaction, this formula to find the Q reactions. Then from there we can just say that the delta H will be the same value. All right. Next, we have another calorimeter. This one is constant pressure. So I just bring out this point here. Just now I said that whenever the reaction is occur at constant pressure, the delta H will be equal to Q. So what answer you calculate using this formula, it will be also equivalent to the delta H. Okay, let me break down to you what is this coffee cup calorimeters. So sometimes they call it the constant pressure calorimeters. So basically we just have two styrofoam cup put together, stacked together, cover it, and we put a thermometer and a stirrer. So this is your sample. So the sample tend to be liquid form. So as you can see, just now bomb calorimeter tend to be in solid form. For coffee cup calorimeter is tend to be in liquid form. And liquid, since we know that liquid, of course, they are using water. All right, because many solutions are using water as universal solvent. So many reactions can be measured by these coffee cup calorimeters. So to name a few, we can have neutralization, we can have heat of solution, we can have heat of dilutions. For these calorimeters, the calculation will be the same. So Q reaction equal to Q water plus Q cal, and then for Q water we are using MS delta T, Q cal we are using C delta T. So next, I will show you a few examples on how to utilize this formula to calculate the Q reactions. Okay, to add on a bit on the on the coffee cup parameter, because it's said to be at constant pressure. So here are some of the reactions, as to name a few, that can be measured by the coffee cup parameters. All right. Because no heat enter or leave the system throughout the process, heat lost by the reaction must be equal to the heat gained by the calorimeters and water. Therefore, we can write Q reaction equal to Q water plus Q calorimeters. So this is your system. This will be your surrounding. So this will be your system. This will be your surrounding. If we are looking at bomb calorimeters, so the Q reaction is combustion, so heat loss, therefore exothermic, and the other part that will be absorbed by the surrounding, so the heat gain will be absorbed by surrounding. In other words, the heat will be absorbed by the water and calorimeter. So the right side will be endothermic. And to emphasize again many times, make sure you know that Q water, we are using this formula. Q cal, we are using this formula. All right, so look at some example here. A reactant was burned in a constant volume calorimeters. Constant volume calorimeter, in other words, it will be your bomb calorimeters. The temperature of water increased from 20.17 to 25.84 degrees Celsius. Given the mass of water is 2000 gram. Heat capacity of the calorimeter is 1.8 kilojoule per degree Celsius. Calculate the heat of combustions. So heat is Q, so I can just call it this one a Q combustion. You want to name it Q reactions also can. All right. One formula that important, so I just call it the Q combustion is equal to formula is there's a bracket there, so outside there's a negative, so Q water plus Q cal. All right. For Q water, you know that you have to use a correct formula. Q water, you're using the ms delta T. So the m is the mass of the water, S is the specific of the water, and the delta T is the one experienced by the water. So mass of the water, so you have to find in the questions. Can you see 2000 gram? So that will be your mass of the water. Specific of the water is a given value, so it's 4.184 joule per gram dot degree Celsius. Delta T, yes, you can see a temperature change there. You take the final minus the initial. All right, so make sure every unit is correct, the value is correct. Okay, then we calculate. So with calculator, 47400 joule. So we'll convert into a kilojoule, 47.4 kilojoule. All right, actually we have solved the first one. So now look at the next one, Q cal. The heat absorbed by the calorimeters. So we are using a C delta T. So the C is the heat capacity of the calorimeter, and the delta T will be experienced by the calorimeters. So C is the 1.80 kilojoule per degree Celsius. The delta T will be the same. So it's a 25.84. Okay, calculate this one. We get 10.2 kilojoule. All right, then we are using this formula again. Q combustion, it will be equal to negative Q water plus Q cal. So put in the value. Q water we have is this one, 47.4 kilojoule plus Q cow is this one, 10.2 kilojoule. Okay, then we get the answer negative 57.6 kilojoule. So this will be your final answer. Okay, let me show you why many students make a mistake in this kind of questions. The first mistake that student make is they didn't convert to kilojoule, especially in this part here. Please take note. All right, because the specific heat of water, they tend to give us in joule per gram per degree Celsius, but the heat capacity, they tend to give us in kilojoule per degree Celsius. So if Q water you didn't convert to kilojoule, so you stick to joule, and this one you stick to kilojoule, and then you add up. Of course the answer is wrong, because joule and kilojoule you cannot add up. Alright, so my advice is to you convert everything into kilojoule. Alright, so just take note that I repeat again, the specific heat of water is tend to give you in joule per degree Celsius, but the C cow, they tend to give us in kilojoule per degree Celsius. Alright, this is actually a much safer answer because we do it separately. So first we calculate the Q water, then we calculate the Q cow, and we calculate the Q. Finally, we calculate the Q fractions. Okay, look at another example here. 0.15 gram sample aluminium solid was burned in a constant volume. So once again is questions on bomb calorimeters. Temperature 0.5 kg of water increase. Given the heat capacity of calorimeter is 1.6 and the specific heat capacity of water is 4.184, calculate the heat of combustion of aluminium. Okay, this one a bit different. They want in kilojoule and kilojoule per mole. Okay, so we are using the same formula here. So first we calculate the Q water. So we are using the ms delta T. So the m is a mass of water. Okay, please take note, we have two different mass here. One is 0.15, one is 0.50. So which one should we use? Alright, since we are calculating Q water, the m will be, of course, is the mass of the water. So we are using 0.5 kilogram. But you know, you cannot use kilogram, so we have to convert. So this one we get 500 grams. Specific of water, joule per gram dot degree Celsius. Okay, delta T is also, you can see in the questions, 59.14 minus 35.23 degrees Celsius. Okay, key in everything here, so we get this answer. And I convert to kilojoule, 50.02 kilojoule. Next, move on. I'm going to calculate the Q cal. So we're using a C delta T. Okay, the heat capacity of calorimeters given 1.60. So as you can see, it tend to give us in kilojoule. Kilojoule per degree Celsius. Alright, the delta T will be similar with this delta T. 59.14. You're going to minus 35.23 degrees Celsius. Why the delta T is the same? Because we only have one thermometer. So any temperature change will be measured by the same thermometer. So therefore, the two delta T here will be the same. Alright, calculate the value. So we get 38.26 kilojoule. Okay, then we will use the formula Q. Okay, the measure is a Q combustion. So you can write Q combustion, or in general you can just write Q reactions. So Q reaction will be negative brackets. Remember, negative in front. So Q water plus Q cal So Q water, put in the value 50.02 kilojoule. Q count 38.26 kilojoule. Okay, total up, add up together, we'll get negative 88.28 kilojoule. So this is the first answer they want in kilojoule. Next, you can see that they actually want us to calculate something in kilojoule per mole. So the kilojoule per mole, so the per mole here is the mole of the sample that you burn. So we are using aluminium solid. So you have to find the mole of aluminium they use. So the mole of aluminium is the mass of aluminium, so 0.15 divided by the molar mass, it gives us 27. So 0.15 divided by 27, we get about 0.0056 mole. Alright, then to find the Q reaction in kilojoule per mole, we'll take this answer, negative 88.28 kilojoule, divide by the mole aluminium, 0.0056 mole. So then we get our answer, negative 15764 unit kilojoule per mole. So these are the two final answers they want. Alright, I hope that you understand this one. Okay, please practice more on the exercise that I put in the times. Any question, please ask me. Alright, thanks.